At the beginning of December 2024, Meta released its brand new open-source AI model, Llama 3.370B. In this video, we'll explore why this model has initiated a small revolution and how to deploy this kind of model to unlock their full potential. Before we dive in, let me give you some context. For those unfamiliar with the Llama model family, these models are part of the category of very large language models, alongside OpenAI's GPT-4, Google's Gemini, and Anthropic's Claude. Among these large language models, some are not open source, GPT-4 for example. This means you can only use GPT-4 through OpenAI services, and as a result, you must send your data every time you use an OpenAI model. On the other hand, some models are open source, which is the case for the Llama family. You can download these models and run them on your own infrastructure. This gives you control over your data, a crucial factor in fields where data sensitivity and regulatory compliance are essential, such as healthcare, law, or defense. Until the release of Llama 3.370B, the highest performing open source model was Llama 3.405B. This model offers a quality comparable to GPT-4o, but is difficult and expensive to deploy due to its 405 billion parameters. However, with Llama 3.370B, things have changed. According to Facebook, Llama 3.370B delivers performance similar to the 405B model, and therefore to GPT-4o at a relatively low cost. With this model, Meta has sparked the creation and sharing of open-source models that are both reasonably sized and capable of matching proprietary models in performance. Following this, DeepSeek released a suite of open-source models of various sizes, ranging from 641 billion to 1.5 billion parameters, achieving state-of-the-art performance. Notable examples include DeepSeek R1 Distill Llama 70B and DeepSeek Distill QN32B. In March, Alibaba introduced QWQ32B, a model with an unprecedented performance-to-size ratio. Finally, Google launched the Llama 3 series, which offers excellent performance-to-size efficiency and high versatility. These models even support image processing. All of these open-source LLM empowers smaller AI players to develop useful and diverse applications. My goal in this video is to show you a generic approach that will help you deploy Llama 3.370B or any other large language model. And as a bonus, at the end of the video, I'll show you how this approach allows you to deploy uncensored models. Now, let's briefly talk about how to evaluate model quality. Typically, when a model is released, its creators share performance metrics across various criteria. For example, you can check Meta's page to see the performance evaluation of Llama 3.370B. The first metric in this table is MMLU, which stands for Massive Multitask Language Understanding. This metric evaluates a model's ability to answer a wide range of questions across diverse topics. Here, we see two columns, Zero Shot and COT. COT stands for Chain of Thought. And basically, what we're measuring on this line is the model's ability to respond without having seen any prior examples. For this criterion, we can see that Llama 3.3 is still weaker than models like GPT-4o or Llama 405, but it's still comparable. Next, there's instruction following. This criterion measures a model's ability to follow user instructions. Here, we can see that Llama 3.3 ranks first, tied with Amazon Nova Pro ahead of all other models, so that looks very promising. Then there's the code human eval line. As the name suggests, this evaluates the model's ability to generate code. The winner for this criterion is Claude, but Llama 3.3 still performs very well here once again, even ranking ahead of GPT-4o. The goal here isn't to go through every criterion, but I still want to highlight another very interesting one, the one provided on the last line. This criterion is the estimated operating cost of these models. We can see that Llama 3.3 costs 25 times less than GPT-4o when receiving tokens, and up to 30 times less compared to Claude, also in the token reception phase, when the model receives the prompt. And when it comes to token generation, meaning when the model actually responds, Llama 3.3 is 25 times cheaper than GPT-4o and more than 35 times cheaper than Claude. So, that seems quite significant. However, these are still Facebook's own measurements, and every creator develops their own evaluation methods, so it's wise to cross-check sources before drawing conclusions. I suggest visiting artificialanalysis.ai, an independent site that provides alternative insights into model quality. On the intelligence benchmark, the top-performing models are OpenAI's O3 Mini and O1, but they are closely followed by DeepSeek R1 and QWQ32B, two open-source models. Llama 3.370B ranks ninth, just behind GPT-4o. In terms of response speed, Llama 3.370B takes third place, outperforming both OpenAI's models and DeepSeek's. When it comes to cost per token, QWQ32B, Llama 3.370B, and DeepSeek R1 rank third, fourth, and fifth, respectively. This site offers a wide range of benchmarks, and I encourage you to explore them to get a better sense of the power of open-source models. The key takeaway here is that high-performance open-source models are now available and can run on reasonably sized infrastructure. Developing AI solutions has never been this simple and accessible. A natural question that arises now is, how can we effectively use these models? There are two main strategies. Rent a machine and deploy the model yourself. Use managed services. Each approach has its pros and cons. Renting a machine provides more flexibility in implementation and provider choices, as well as lower operational costs, since you're only paying for the machine, not additional services. However, unlike managed services, you are responsible for keeping the model running, handling scaling, managing workload spikes, and maintaining the system. This requires strong technical expertise. Since this is an engineering-focused channel, we'll go with the first approach, renting a machine and deploying the models ourselves. Now the question is, what kind of machine do we need to run these open-source models? To run LLMs efficiently, a machine needs powerful GPUs, lots of VRAM, this is the GPU's dedicated memory, plenty of RAM, significant storage space. You'll notice I didn't mention CPUs. While CPUs are important, they are not a critical factor. The real bottlenecks and biggest cost factors are the GPUs, VRAM, RAM, and storage. To determine how much VRAM is needed to run Llama 3.3 or any other LLM, we first need to understand how LLM weights are stored. And overall, there are 4 ways to store weights for LLMs: FP32, FP16, INT8, and INT4. First, FP stands for floating point. FP32 means using 32 bits to store each network weight, FP16 uses 16 bits, INT8 uses 8 bits, and INT4 uses 4 bits. Generally, FP32 is used when high precision is required. FP16 offers a balance between precision and storage size, while INT8 and INT4 are used when optimizing model size is a priority, at the cost of lower quality and precision. Here is a table summarizing the necessary VRAM for Llama 370B and Llama 3405B based on floating points. If we choose FP32, 32-bit, we must multiply the number of parameters by 4, as 32 bits equal 4 bytes. So, multiplying 70 by 4 gives us 280 GB, meaning we need 280 GB of VRAM to run Llama 370B in FP32 with very high precision. If we reduce weight storage precision slightly by switching to FP16, we only need 140 GB of VRAM. With INT8, we need 70 GB, and with INT4, just 35 GB. Comparing these numbers to the VRAM needed for Llama 3405B, the difference is massive. Now, how much RAM is required to run this model? Unlike VRAM, there are no strict theoretical rules for RAM requirements since it depends on the LLM's characteristics, usage patterns, and load. Factors like the number of users and request handling mechanisms, queues, etc., influence RAM needs. However, a common empirical rule suggests needing 2 to 3 times the number of parameters in RAM. Applying this, Llama 370B would require between 140 and 210 GB of RAM. Again, comparing with Llama 3405B, the difference is huge, between 810 and 1215 GB of RAM. Next, let's look at the required disk storage. There's no strict rule here either, but a rough estimate is about 5 times the number of parameters. Multiplying Llama 370B by 5 gives 350 GB, and for Llama 3405B, around 2 TB. Now that we know what kind of machine is needed, let's check pricing, starting with AWS. Instances are ranked from most to least expensive, with P5e being the most costly and G5G the cheapest. Looking at G4 instances, we see they use NVIDIA T4, but VRAM details aren't available, so we move to G5, which features a 10G GPUs. Here we find GPU memory VRAM, and to run Llama 370B, we would need a G548X large instance with 192 GB of VRAM. 768 GB of RAM, more than enough, and storage of 2 times 3800 GB, also sufficient. Now for the cost, $16 per hour. Comparing with another instance, G6, which is slightly smaller but also offers 192 GB of VRAM, the price drops to $13 per hour. Looking at G6E, which offers 192 or 384 GB of VRAM, prices aren't listed, so we check P4 instances. These offer fewer options, but the first one has 320 GB of GPU memory and costs around $32 per hour, more expensive due to higher GPU power. In summary, AWS costs between $13 and $32 per hour, depending on the instance type. Now, let's check Runpod, which also provides GPUs. Runpod offers various GPUs, including H194 GB VRAM, H200, 142 GB VRAM, and AMD with 192 GB VRAM. GPU pricing for groups isn't displayed initially, but after logging in and filtering for GPUs with at least 288 GB of VRAM, multiple options become available. Runpod groups similar GPUs like AWS, but it's significantly cheaper. For example, renting 4 A100 GPUs costs between $6 and $8 per hour, much lower than AWS, where A100 costs over $32 per hour. The savings are massive. 192 GB VRAM, AWS was around $16 per hour, whereas Runpod offers much cheaper options. The MI300X costs $3 per hour, RTX A5000 also $3 per hour, and 4 A40 GPUs cost just $1.56 per hour. While these options look good on paper, testing is necessary to confirm model performance. It's always best to test before committing. Additionally, AWS imposes access restrictions, requiring approval for GPU, a process that can take time. In contrast, Runpod offers instant access as soon as you add funds to your account. For our case, we will use Runpod instead of AWS. We'll use 4 A100 PCIe GPUs on Runpod and configure them by editing the template. We'll allocate 300 GB to both disk storage and volume, expose port 8000 for the model and port 22 for SSH connections. Checking the instance summary, Runpod calls it a pod. We see RAM, VRAM, and total disk size before deploying. The deployment process may take a few minutes. Once deployed, we can check GPU activity logs and connect to the machine using SSH or a web terminal. The simplest way is to open a web terminal directly. Since we'll need to install various libraries, we first run apt-get update. Then install the vLLM library for deploying our LLM. While installing, let's check out vLLM's website to understand its functionality. vLLM is a library for inference and serving. In LLMs, inference means generating text from a prompt, while serving refers to running a web server that makes the model accessible via API requests. vLLM boasts state-of-the-art performance in handling high request loads. It also optimizes attention mechanisms and allows continuous request batching. We can perform quantization, which means converting from FP32 to int4, for example. So we can see that this library contains many tools. It's extremely comprehensive and allows for optimized deployment of our LLMs. Plus, vLLM is very easy to use. Later, we'll see that we can directly use models available on Hugging Face. To install vLLM, the easiest way is to run a pip install, just like we did earlier. Next, we will use vLLM with the OpenAI server approach. So we'll run our command line with vLLM serve. Then we need to specify the model name. The name is retrieved from Hugging Face, and it will automatically download the model from there. Next, there's the D-type. Here, it's the floating point type. If we leave it as auto, vLLM will choose the appropriate D-type based on our machine specifications. If we want to specify it manually, we can choose FP32, FP16, or int8. Then there's the API token, which corresponds to the authentication token used to authorize requests. As I mentioned earlier, vLLM launches a web server where the model is accessible via API requests. Without an authentication token, anyone sending a request to our API could use our LLM. So to add some security, we use this authentication token to verify who is making requests and who is allowed to use our LLM. Next, we are given a basic Python script for making requests to our server. In this script, we find the URL where our model is accessible. We will need to modify this URL since it will be our pod's URL instead of localhost. However, note that port 8000 is specified, and if you remember, we opened port 8000 on Runpod earlier. The script also includes the API token to ensure the request is accepted by the server. This token must match the one we defined earlier. Additionally, we specify the model name since vLLM allows multiple models to run on the same machine and URL. Therefore, in our request, we need to indicate which model we want to use. We also include the prompt, with the role set to user. This example is very basic, but we can add numerous options on both the server and client sides. These options allow us to build a tailored and high-quality application. Below, we see a long list of available options. Before going back to our pod, I wanted to briefly discuss deployment. What we did here is the simplest method using pip install, but there are other approaches. For example, we can use Docker to containerize our vLLM server, which is very useful for CI/CD or DevOps. For scaling, you can use Kubernetes. This provides the benefits of Docker while dynamically managing user load. Here, we see the cluster configuration, which can be a bit complex, so I won't go into details. However, I could make a video on this topic if you're interested. Let me know in the comments. You can also use Helm to simplify Kubernetes cluster configuration. And if you don't want to use Kubernetes, you can scale vLLM with NGINX and a load balancer. We won't go through all the details here, but you can see that the setup is highly flexible. You can also monitor your system to check if everything is running smoothly or if you need to increase computing power due to resource saturation. This library is truly designed for deploying LLMs in production and efficiently managing your entire application. Now that vLLM is installed, the next step is to log in to Hugging Face because we'll be downloading Llama 370B from Hugging Face. To download this model, prior authorization from Meta is required. So to proceed with the download, Hugging Face requires me to be logged into my account. Hugging Face then asks for my authentication token, which I provide. I select No, and now I'm successfully logged in. The next step is to use vLLM to launch Llama 370B. Here you see that it only takes a single line of code. We pass parameters such as the model name, dtype, API token, and tensor parallel size, which represents the number of GPUs on our machine. In this case, we have 4 GPUs, so we set it to 4. We can see that the model is being downloaded. Initially, it downloads the tokenizers and model configuration, followed by the model itself. The model is quite large, but the download speed is good, around 25 MB per second. However, each file is about 5 GB, and since there are 30 files to download, it will take some time. Once the model is downloaded, vLLM deploys it. While that happens, we can monitor our machine's activity directly on Runpod. Here, we see that the GPUs are fully utilized and the GPU memory is almost at full capacity. This is an intensive process. Now the model is deployed. Uvicorn exposes port 8000 on our machine, which, if you remember, we had opened earlier when starting our instance. This is the port where we'll send our API requests. Here we click on Connect HTTP because we'll be making HTTP requests to our server. Runpod provides us with an HTTPS URL, which we will use for our requests. We follow vLLM's instructions and use the OpenAI format. We take the HTTPS URL and set it in base URL. You can see that it's correctly formatted as HTTPS. We then specify the model name, which is Meta Llama 370B instruct. Now we can send our request. We receive a response. Hello, it's nice to meet you, blah, 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 blah. So we're happy it works. Now let's ask something more complex, like generating a Python script that sorts n integers with n log n complexity. We check our machine's activity and see that it's running intensively. Looking at the logs, it seems we've received a response. The model has returned a script for sorting n integers in on log n using Python. It looks promising, though we won't read the entire output. But we can see that it mentions the merge sort algorithm, which indeed has O n log n complexity. However, I just realized a small mistake. I wrote n for integers and n log n in different cases. Ideally, I should have used lowercase n consistently. I suggest we stop testing Llama 370B here. But before moving on to the bonus section of the video, I want to add one last point. In this setup, we use the OpenAI client to send requests to our server from a Python notebook. However, in a real production environment, your LLM will most likely be used by people through a web or mobile application. This means requests will come directly from applications rather than a notebook. Making requests to our vLLM server without the OpenAI client is also very simple. You just need to make a post request to our machine's IP's address at port 8000/v1 chat completion. For authentication, we need to include our authentication token inside the request. And in the request body, we provide the same elements as in the OpenAI client, namely the model name, the role of the person making the request, and the prompt. I've included a very basic example of a request using curl, and I'll run it directly in my terminal, but you can make the same type of request in a web application, for example, using Axios. And while I was talking, we received the result of the request, so everything is working as expected. Now, let's move on to the bonus section and take a look at how to deploy uncensored models. In my opinion, the most well-known uncensored models are those developed by cognitive computation, particularly the Dolphin family. Here's an example of what these uncensored models can do. We see that a user asks how to make as much noise as possible with their Honda Civic for €200. Instead of telling them that making noise with their car is not good or that it can't help with that, the model actually provides steps to achieve the goal. Beyond being quite funny, this uncensored behavior can be useful in certain types of applications. So let's see together how to put this kind of model into production. And there are many uncensored models. If we go to the cognitive computation page on Hugging Face, we can see the list of their uncensored models. We find models from Mistral, as well as models from the Llama family. For a change, I suggest using this model, the Mistral 7B model, which has 7 billion parameters, and trying to put it into production. Based on what we saw earlier, a model with 7 billion parameters requires 28 GB of VRAM if we want to work in FP32. Two RTX 4090s should be good enough and are one of the cheapest configurations. For just under $2 per hour, we get 48 GB of VRAM and 92 GB of RAM, which seems theoretically sufficient to run this model. As with Llama 3.3, we need to edit the template. I suggest allocating 120 GB of disk space. That should be more than enough, 120 GB for storage. And don't forget to open port 8000 because, as a reminder, vLLM launches the web server on port 8000. Next, we see the configuration summary and the price of our pod, and we just have to launch it. Like before, let's keep it simple. We'll connect via the web terminal, even though we could do it via SSH. Once we're in the terminal, we run apt-get update, then install vLLM, just like before. Here, there's a small difference compared to earlier. We don't need to log in to access the model because Dolphin models are completely public. So, we can directly run the command vLLM serve. And here, the only difference from earlier with Llama 3.3 is that we change the model name, which we get from Hugging Face. Now we only have 2 GPUs instead of 4. We press enter. vLLM fetches the metadata and downloads the model. And now, vLLM has started our web server, making our model available on port 8000. Just like before, to use our model, we need to retrieve the URL of the pod. We modify the URL inside our OpenAI client on our notebook. We just have to change the model name. Now, we can modify the prompt and ask how to steal an egg from our children. You see, the word steal is in this request, which could block some LLMs. We're hoping to get a response that actually tells us how to retrieve an egg. Now that we have the response, it turns out this model is still somewhat censored because it refuses to help us steal the egg. So I suggest testing another model, and we'll take this opportunity to see how easy it is to switch from one model to another with vLLM. Looking at the list of models, let's pick Llama 38B, an 8 billion parameter model. Theoretically, our pod is powerful enough to run it and has enough memory. We use vLLM serve and we just need to change the model name. vLLM downloads the model again and starts a web server. Back in our notebook, you're probably getting used to this. We check the URL, change the model name, and then modify the prompt. Once again, we ask how to steal an egg from our children. And now, we see that the model responds. It provides a strategy to steal the egg. So this model seems to be uncensored. It doesn't block on the word steal and even gives us a tip, suggesting that we wait until our children are at school. Now we could ask much more advanced questions, but I'm afraid YouTube might block the video. So let's just change egg to car and see what happens. The response confirms that our LLM provides a strategy. But if we now ask the same question on ChatGPT, it won't help us at all. So as you can see, this is quite interesting. We can do a lot of things. We've reached our goal, so let's end the video here. I hope you enjoyed it. If you did, please like the video and subscribe. See you soon for another video. Bye.